Numpy is all about numerical computing, and computing is mainly based on math. So in this video we'll talk about how we can perform math with Numpy arrays. And our main tools here are math operators and functions. We can differentiate operators and functions because operators perform operations on objects, such as for example two numbers. So for example addition is an operator, or subtraction, and functions represent the relation between two objects. So for example sine or cosine, or the exponential function. And we can view some functions as operators, but not all of them. So in here we will first cover operators and then functions. And in Numpy, the math operators and functions are implemented as ufuncs, which is short for universal functions. And we say universal because with them we can perform a variety of operations on basically any array. And they are the fundamental building blocks of Numpy's array processing capabilities. And these universal functions operate element-wise on arrays. Now, element-wise does not mean that we have to use Python's slow for loops, but it's more conceptual. So when we create these arrays here, which are just the values from 0 to 9, and then we perform addition, so we add +2 to our array A, then the 2 will be added element-wise. And now the cool thing is that these ufunctions are vectorized. That means that the element-wise operations can happen for multiple elements at once. So you don't have to add the 2 to the first element and then to the second element, but it all happens all at once, and it also happens in C. So in the background, Numpy is offloading the calculation to C, which is another much faster programming language. And so this way we don't have to rely on Python's slow looping. Okay, so besides adding 2 to our array, we can also add 2 arrays together. We can also subtract from an array, and again this all happens element-wise. Same for subtracting arrays from each other, also element-wise. Same thing for the multiplication. And here it's especially important to note that this operation will be performed element-wise, because you might expect that multiplication between vectors or arrays would be seen as matrix multiplication, but for that we actually have a proper operator, which is the add sign here. So before we come to that, we also have the division, which also works element-wise just as expected. And then now the matrix multiplication is done with the add operator. So this gives us then the dot product of these two arrays or vectors. Okay, so much for the operators. Next up we have the mathematical functions. And of course we're not listing all of them here. You can check out the rest by clicking this link here. So for example we have the np.sine, the sine function, the exponential function, the logarithm, and also the logarithm with a base of 2. So the normal logarithm here refers to the natural logarithm. And again, everything happens element-wise. Next up are comparisons. And for the most part, these all work like we would expect. So we have two arrays here, and some values are equal and some are not. But we can already see there's something special going on, which is the d-type at the end here. So these two arrays have a different d-type. Up here we have float 32, and down here we have float 64. And so in this level we're computing 1.2 minus 1, which you would expect to be 0.2, but it's actually not due to float point imprecisions. So our value here is a float, and because of how floats work, they're sometimes not 100% precise. And so the thing is, the more bits we use to store our values, the more precise the result becomes. So if we run the cell here where we create the arrays with that value here, and then we can look at these two arrays, and then we compare both of them, we can see the value in these two arrays is actually not equal to each other. And this is because they have a different resolution, so to say. We can also check that by accessing the element, and indeed they're not equal. To address this issue, we can use np.isClose, which will take two arrays and then compare each of the elements with each other, and this time not check if they're perfectly equal, but just if they're close enough. So we run that, and then also the first element will be equal. And if we look at the function's parameters, we have some options of defining when two values should be equal or when they shouldn't be. Okay, then other comparisons are the not equal, which works like expected. We have smaller and greater, also smaller and greater equal. And now a small note about np.nan. So if we're dealing with missing values, then it's important to know that two missing values or two undefined values are not equal. And that also means that if we want to check if something is missing, we need some other functionality. And for this case, we have the np.isNan, and we can run that on our value, and this will then tell us if a certain value is missing. Next up, we have the function all. And this function can be used to check if a comparison is true for all elements. So here we have two arrays which are the same, and then we compare them we add the .all, and this will obviously tell us true, because all the elements are equal. Now there is something important to watch out for, because if we have an empty array and an array with one element, then the comparison will also return an empty array. And according to the all function, there's nothing false in here, so it will actually return true, even though these two arrays are obviously not equal. So you have to be careful here. And then similar to the all, there's also a any function. And this will check if a given comparison is true for any of the array elements. So in here, only the 3's are equal, and so we compare the arrays and append the .any, and this will then tell us true. Okay, now finally a short look at constants, which can be useful if we're doing any kind of mathematical operations. And so some of the constants are pi, e, and also infinity, which will be bigger than any number that we can type. And by adding a minus sign, we can also get minus infinity. Now you might be curious what happens if we subtract infinity from infinity, but because this doesn't really make sense, Numpy actually gives us a missing value.